but I'll be talking only once. Okay. So thank you for your invitation. I'm also very grateful to the colleagues from Spain, and especially a lot of work done by Raquel and her colleagues. So many sites and so on. I would say I will be talking only about two sites. In fact, I would like to summarize some experience based mainly on our prefeasibility studies. So the contents of my presentation is like this. First, few words about replication study concept. It is in fact known. A few words about hydraulic energy recovery machines that we took into account. Of course, part was most important. In this introduction part, also something on part-based energy recovery systems, and two case studies on which I'll discuss some our experiences, some discussion and conclusions. Of course, the concept was to reproduce this, what is here in Porma, but we didn't took into account electrochemical batteries. We took into account both drinking water treatment plants and wastewater treatment plants, although our experience with drinking water treatment plants was better. But in Poland, we have also good opportunities in wastewater treatment plants. So you can see here the map of Poland with this, with some sites. I'll concentrate these sites with white interior inside circle. These are those that I will be talking about. So of course, so we took into account the hydraulic energy recovery systems and with drinking water, with classic turbines, as you can see on the left. There's the existing equipment, classic Francis turbine in an installation that we visited. This is several hundred kilowatt. Then real in-conduit turbine, which is installed also in the south of Poland. We consider, of course, the alternative are parts, and some advantages were already discussed here. Yes, working KSB pump in one of our water intakes in the south of Poland, and we took into account also wastewater treatment plants and proposed in one of them using just a tubular turbine, but this is always at outlets, not at inlets to the wastewater treatment plants. So as you perfectly know, we concentrated on pumps as turbine. As you know, these are considered feasible for medium currents between 10 and 100 meters. The range is usually starts somewhere with tens of liters per second up to tens of cubic meters per second. In comparison with classical turbines, they are a little bit less efficient, but the main problem is regulation, and I talk a little bit about it. In fact, our assumption was that when we introduce energy recovery machine, we should reproduce the same graphic this discharge graphic, the time course, as it was before. In reality, it can be different, but in simulation, we assumed nothing will change at the distribution, municipal distribution network. So, in fact, in this case, you have variable discharge, and this is really a problem. At the first time, I thought, or we thought, we can just regulate the speed, but it is really not the case, as within the range which you are interested, we use centrifugal pumps, and most of you probably know that speed regulation is not very good, as they resemble Francis turbines, and you can see on the right side possibilities simulated for when you use speed regulation and when you use just simple throttling. The possibilities with throttling are much higher. So explanation is, of course, in the curves of Francis turbines. You can see that if you take such hill diagram, the curves, discharge curves, are almost horizontal or even falling down, depending on the specific speed. It is different with propeller turbines, but in this case, they are not so often used in energy recovery systems, as they are meant mainly for lower heads. Here it is possible. You can see here the discharge versus rotation speed at various heads. However, if you take some centrifugal pumps, it is quite often that the curve is flat, so changing the speed doesn't give much. So this is the reason why we used also part with throttling. You can see typical curves that you know, characteristics. Usually there are three curves. That is one as to run away, that it's the torque is equal to 0. Then you have the second one with 0 0 speed. That is, the machine is stopped, and this is the discharge. Of course, the efficiency is also 0, as you have no speed, and you can have just a bundle of curves with different speed. If you ask KSB or some other company offering parts, you'll receive the speed that is recommended, or this is the rated speed. So we followed a recommendation of our Spanish colleagues, but also we knew for long decades, I would say, that KSB is dealing with the problem and is offering PAT turbines, and we decided that throttling will be used. In fact, you can see an example, two operation points which are located up and down of the performance characteristics. Of course, you cannot increase the discharge. What you can, if you are above, the only thing that you can do is to throttle in parallel with your PAT. If you have too little head is below. Yes, if you have high discharge, but the head is too low, the only thing to do is to use a bypass. So this is an example. You can see here also a relief valve. The valves that we selected, these are the valves usually used in water treatment plants. That these are membrane valves, and you can see the typical scheme with such three valves. I pay your attention on valve number valve Z1, that is in parallel, and Z2, which is in row with PAT, and the control ranges are shown. Usually these valves operate are controlled by the pressure downstream of the valve. It can be also the pressure transducer can be also in some other site which we used in fact. So the first our case study was close to Krosno in the south of Poland. You can see location on the map. Water is delivered here by some 14 kilometers long pipeline, but it is of very high diameter, so there is not such a major risk of hydraulic transients. Here is the system. There is municipal network, and here is a chamber in which you have to reduce the pressure from about 9 bar down to 4 bars at the entrance to the municipal network. It is not so, in fact, the discharge changes, and we had also drinking water treatment plant there, and probably this will be not used. Our proposal as drinking water treatment plant now is getting again in operation. Previously, they planned to stop it completely, and the water network operator was highly interested in. You can see these are situations when the drinking water treatment plant is in operation, and now this is typical flow flow duration curve, and these are typical operation points. These two clouds and the two regimes. I don't know what happens. Yeah, but okay, it is not so important. This is what we proposed. In the next case, we'll show you also the relief valve, but in this case, we had the situation that the existing membrane valve is sufficiently swift, and the height of hydraulic water hammer is not is very limited due to high diameters. We have checked it. So the discharge here is 210 cubic meters per hour, head 50 meters, and we expect 22.7 kilowatt. We selected such a unit. At the end, we should 4 bar at the inlet to distribution network. We have calculated also annual generation. It should be 65 megawatt hours. But what is important, we took into account we used the data from the utility, and in both these cases under consideration, I can say that we use something like 40. We are able to use something like 40% of the raw energy. We assumed 75, but in fact due to throttling with when we can which we have to apply, and due to hours in which we cannot use the part due to parameters, it is only 40%. So if you look at our this payback time, discounted payback time, as you can see, it is 14 years. But I don't know what was your time. It was simple payback time, or so simple payback time is 7 years. It is with internal return rate 11%. The other case is Murowanec Reservoir. It is in Zakopane at foothills of Tatra Mountains. You can see enormous scatter in the data. We don't quite understand why it is so high. We try to understand it better, but I have a feeling the utility that is not. I don't know how it happens that you cannot see anything on the left, but this is the flow duration curve, and this is the solution that we proposed. In this case, we have also throttling in parallel and in row. In fact, I should have said that this is a pressure reduction chamber to the storage tanks, and water flows to the network already from the storage tanks. So the pressure limitation at the inlet is follows only from the need to keep the pressure not too high when it flows to the open surface tanks. So it was something like 1.5 or 2 bars, not more surely. I don't remember. It is over pressure. Oh, it is written over pressure should be 2 meters. So the flow is not too high. Annual generation is much higher, but the head is average head, and average distance at the time when we can use it. In fact, heads is sometimes much higher, but this time we had to use additional additional relief valve, as the valve number Z1, which is on the main pipeline, is the one previously used, and it is not fast enough to operate during water hammer. In fact, if we open Z3, depending on the pressure P1, we can avoid problems. I would say that the problem in these cases is not only due to hydraulic tension somewhere upwards, but also from voltage outage, as in fact, then you have run away of your machine, and it goes and the discharge falls very swiftly down. These are the duration of this process is below 1 second, so you should be very swift in opening your relief valve, and it is possible if you use membrane valve. So in this case, it is also, I have not written down a simple payback, but it was also something like 7 years, I remember. But if you take into account such discounted payback, it is much more. These are typical diaphragm actuated automatic valves that you use also here. And we had to choose between various options. Plunger valves, which are a very high price, Luger valve, which is now they are in Zakopane, but which is first of all brings high hydraulic losses. So far as there was no energy recovery, it was of no significance. And secondly, it is also, well, it can be fast, but losses are immense. And butterfly valve, which as it is now, has very poor cavitation properties, and also there's a problem. High losses when it is open. It is no problem when it regulates, but when it is open, the losses are a problem. So we received also such cavitation characteristics from the company. I would notice that that such a configuration gives us also opportunity to increase efficiency of the whole process by properly operating the machine, while it elongated the operation time of the unit, recovery unit, but I will not go into details. I would say, just summarize, understanding the need of energy effectiveness, including recovery of hydraulic energy dissipated in municipal and industrial water sectors, is rising. However, promotional efforts and systematic identification of new opportunities are needed. I would like to notice that we had some problems with economic calculations due to regulations, as they treat quite often micropower sources, as all of them were solar batteries or wind turbines. They want, for instance, expect either additional storage or at least frequency converter. This has an enormous impact on the price. So we as association will fight against it, because it is nonsense, as hydropower sources are just controllable, and they help to stabilize this system. So of course, fair and reliable feasibility studies are crucial. Adapting to existing constraints and high safety and reliability requirements are important components. They are more important here than in classical hydropower plants. Parts can be truly considered reasonable in case of powers up to 100 kilowatts, when one had no problems with regulations. Always reliable records of energy recovery site is important, proper understanding, and so on. I would like to end. Thank you for your attention.
Ahora sería